Welcome to today's lecture. In this lecture, we will deal with the unit 3, that is free and forced vibrations. And today's lecture will deal with the free vibrations. In all, we discuss the basics or definition of free vibrations, and then we will discuss in detail the undamped vibrations. What are free vibrations? A body set into vibrations will continue to vibrate with a natural rate of vibrations. And such vibrations of a body with a natural rate of vibrations are called as free vibrations. These free vibrations of a body depends upon dimensions of the body, for example, length, mass, etc., etc. And it depends upon elastic constants of the material of the body. As an example, we consider a simple pendulum. Simple pendulum, we know that vibrates under the action of gravity with a definite period, and this period depending upon the length of the simple pendulum. Moreover, the amplitude of the simple pendulum depends upon initial supply of the energy. More the energy, more will be the amplitude. But in practicals, this amplitude decreases due to the resistance offered by the medium to the motion of the simple pendulum. In this way, the amplitude continually decreases, and such type of vibrations where amplitude decreases continuously are called as free damped vibrations. But if we consider no loss of energy due to friction or resistance of the medium, then amplitude of the simple pendulum will remain constant. In other words, the simple pendulum will continue oscillate with a constant period and amplitude. Such oscillations with constant period and amplitude are called as free undamped oscillations. And here we will discuss the free undamped vibrations or free undamped oscillations in detail. For this, we will discuss in detail motion of a simple pendulum. When a simple pendulum displaced from its stationary position and it is released, then what happens? It will return to its stationary position, and it is due to the restoring force working on the simple pendulum. The restoring force will pull the simple pendulum to its stationary position. Once it acquires its stationary position, it will not remain to the stationary position because it has acquired the momentum. So it will not stop at the stationary position, and it will carry the bob of the simple pendulum to the other end, where whole kinetic energy will convert it into potential energy. That means kinetic energy becomes zero. That means velocity becomes zero. So this is a rest position. Though it is a rest position, the bob will not remain at this position. It will remain. Bob will not remain at this position continually, but it is a momentary rest position, because the restoring force will again bring it back to the original stationary position, and here the momentum acquired will not keep it constantly at this position, and it will move other end, and in this way to and fro motion of the bob of the simple pendulum continue. Okay, what happens here is that when the bob is at extreme position, it has zero kinetic energy, whole energy is the potential energy. and when bob is at its stationary position or mean position, the whole energy is the kinetic potential energy is same. In this way, interchange of kinetic to potential energy, kinetic energy to potential energy from stationary position to extreme position, and when from extreme position to stationary position, the exchange or interchange of kinetic energy from potential energy to kinetic energy. So interchange of kinetic energy to potential energy and vice versa continually took place, and motion of the bob of the simple pendulum continues. So same example is explained here by the graphics. So here this is a position, this is a stationary position of the simple pendulum, and when it is displaced from a stationary position and it is released, so what happens, it will move to its stationary position due to the restoring force working. Okay, and here since it has acquired momentum, it will not remain at the stationary position, it will move to the other position. Okay, here at this position the whole potential kinetic energy is converted into potential energy. That means kinetic energy becomes zero, that means velocity is zero. So this is the momentary stationary position, where restoring force again take it back to the stationary position. Now in coming from the extreme position to the stationary position, the potential energy whole converted into a kinetic energy, and here the velocity is maximum, the momentum has been acquired, and it will move. With this momentum it will move to the other extreme position. Okay, and in this way the to and fro motion took place. So when going from extreme position to the stationary position, the whole potential energy converted into kinetic energy, and in going from stationary position to the extreme position, whole kinetic energy converted into potential energy. So interchange of potential energy to kinetic energy and kinetic energy to potential energy took place continuously, and the to and fro motion of the simple pendulum continues. So here it is the GIF image showing the to and fro motion of the bob of the simple pendulum. Important one is that the amplitude as well as period everywhere is constant. So these are here the internal the frictional force of the medium or resistance of the medium is considered to be zero. So therefore amplitude and period of the simple pendulum remains constant. So as you can see here, the same is expressed in the wave pattern, where you will find that amplitude of the simple pendulum is constant, and again the period is constant because distance between the two peaks is same. So this is a wave, and on the time scale you will find that the time required for the wave is same. So these are the undamped free vibrations, where the resistance due to medium is considered to be zero. There is no resistance of the medium, or there is no resistance of the medium like frictional force, etc. If this friction force exists, resistance of the medium exists, then what happens? The amplitudes will continually reduces, and the time period also continuously increases, and in this way you will find that the oscillations are the amplitude of the oscillations reduces continuously and period is increasing continuously. So these are not the undamped vibrations. Okay, so but these are the vibrations. Okay, all these three figures indicates the vibrations where the amplitude and period remains constant. So these are free undamped vibrations. Now assuming that neither the energy is received and nor it is dissipated into heat by friction, etc. So we will consider here that the kinetic energy and potential energy is constant according to law of conservation of energy. And if we consider such a conservative system where the mass of the system mass m is under the restoring force per unit displacement k, then we can express the kinetic energy as equal to half mv square, where v is velocity, and if y is displacement, the velocity will be dy by dt, rate of change of displacement, and in this way kinetic energy is equal to half m into dy by dt whole square. Let us call it as equation 1. And potential energy simply equal to half k into y square. Okay, so let us call it as equation 2. Since there is no supply of energy and there is no loss of energy, okay, then we will say simply that it is a conservative system where summation of kinetic energy and potential energy is constant, and if we put the values of kinetic energy and potential energy, the summation will be half m into dy by dt whole square plus half m ky square, and this will be equal to constant. Let us call it as equation 3. Now if we differentiate this equation 3 with respect to time, you will find that here the factor dy by dt is taken common, and it will, okay, reduces to 0 after transferring to right hand side of the equation. And after solving this equation, we will find that this equation reduces to m into d2y by dt square plus ky equal to 0. Let us call it as equation 4. And when we divide whole equation by m, then we will find that d2y by dt square equal to k by m into y equal to 0. So this is the differential equation of undamped free vibrations. This equation 5, which is differential equation of undamped free vibration, is similar to the differential equation that is d2y by dt square plus omega square y equal to 0. Let us call it as equation 6. So these two equations are similar, where omega square is simply equal to k by m, and in this way the equation to this differential equation, that is expressed in equation 6, this is a differential equation of a simple harmonic motion, and solution of this we know it is equal to a sin omega t minus alpha. Here simply we have to substitute in this present case for undamped vibrations as omega equal to under root k by m, and we find that displacement of the undamped vibrations is equal to a sin under root k by mt minus alpha, where alpha is constant and it is called as initial phase of the undamped free vibrations. And what will be the frequency of oscillation? It will be angular frequency divided by 2 pi. So 1 by 2 pi under root k by m. So in this way, frequency of oscillation totally depends upon force constant and mass. So with this we conclude the undamped free vibrations. Thank you very much.